Good evening, everyone. My name is Rohan Jadhav, and I'm the TA for problem solving in live sessions for polymer reaction engineering course. I'll be showing you some sample problems where we will discuss them and which will help you solve the assignments, weekly assignments. So, starting from the first question, we have uh, does cooling rate affects the crystalline nature of polymers? Now we know that polymers are crystalline, semi-crystalline, or amorphous in nature, and how they are processed and made is like from a high temperature they are cooled down to ambient temperature, and that's how they gain their crystallinity. And what happens during that process is when the polymer is in the melt phase, or as you can see, when the temperature is very high, they are first cooled down and then they are brought to this rubbery state, which is just uh, in front of glass transition in this diagram, as you can see. And as they are cooled further down, what happens is uh, you can see on the diagram on the right hand side that the amorphous regions right here, right, they start aligning themselves into crystalline regions like this. What happens is they start coalescing together and then they form these crystalline regions like this. And what happens is these crystalline regions then stack together to form to give the crystallinity to the concerned polymer. In case of you can see HDPE or LDPE, the, they are the same polymers, but they have different degrees of crystallinity. Like LDPE is not as crystalline as HDPE. HDPE, because of its crystalline nature, has high tensile strength and better impact properties. And that's why how cooling rate affects this is that if you cool the polymer very quickly, these amorphous regions or the polymer chains won't have enough time to fall into places and stack themselves together to form these small crystalline regions. And they will and what this results in is that the polymer which is suddenly cooled will be amorphous in nature and it won't have high crystallinity. It will be semi-crystalline and it will be very weak. It won't have the desired properties of a polymer. When you cool the polymers very slowly, when the cooling rate is slow enough, what happens is these amorphous regions just come together slowly, and they arrange themselves into these crystalline regions, which results in a proper strong polymer. You can see here, uh, as as the temperature reduces and as the polymers come together to form the crystalline region, the polymer's modulus or the stiffness increases. Why? Because since it's becoming crystalline in nature, it starts arranging itself and entangling itself into crystalline orderly fashion, because of which the polymer becomes hard. And then as it reaches the ambient conditions, the polymer is a hard, hard polymer in its glassy state. So these two diagrams can explain how cooling rate, with respect to temperature, cooling rate affects the crystalline nature of polymers. Moving on, we have how does tacticity affect the properties of a polymer? Now, what is tacticity? Tacticity means what is the arrangement? What is the arrangement of the polymer chains? You can see here, uh, there is an example given right here that about for atactic, syndiotactic, and isotactic polymers. You can see here that in atactic polymers, the functional groups are scattered across in uneven order. You can see two groups right here. See the CO groups are on this side, one is on the other side, one is on again this side. There is no orderly fashion here. So it's like they're scattered around. Then next we have syndiotactic polymer. In syndiotactic polymer, you can see that all the functional groups are present in an alternating way. Alternating. You can see C double bond O on the left and the right hand side simultaneously. As you can see, as you go front through the chain, you can see that they are arranged simultaneously. Hello, am I audible? Uh, I'll be proceeding with the class, and we'll be discussing the questions, sample questions, so that you'll be able to solve your weekly assignment. I'll just brief you on the first question itself. How does cooling rate affects the crystalline nature of a polymer? When polymers are present in their melt form, all the polymer chains are free to move around because of the heat. So, and as you start cooling it, as the temperature reduces down, these polymer chains starts arranging themselves in crystalline portions like this, as you can see in this diagram. It goes from amorphous region to crystalline region. So what happens is it arranges itself in a crystalline fashion and it starts gaining uh, hard properties in the sense like stiffness increases. As you can see, stiffness is on the y-axis, and as the temperature reduces, the stiffness increases drastically beyond this certain point called the glass transition temperature. So when the rate of cooling is very high, what happens is this amorphous region does not have enough time to uh, to correct itself to form crystalline regions. Because of which, what happens is the polymer remains amorphous and the polymer remains amorphous and it won't gain crystalline properties. It will remain semi-crystalline in nature and it might become very brittle and easy to break. So that's why when the cooling rate is slower, what happens is amorphous regions slowly come together and form crystalline regions like this, because of which the polymer chains properly entangle with each other, giving more stiffness to the material. So cooling rate does affect the crystalline nature of the polymers. So moving on to the next question, we have how does tacticity affect the properties of a polymer? Now, what is tacticity? Here you can see the example, atactic polymer, syndiotactic, and isotactic polymer. So here you can see how the functional groups are arranged. You can see they're scattered throughout. Like C double bond O groups are present on two C double bond O groups are present on the right side, and one is on the left, right, left, right. Like there is no proper set order for this. Whereas on the other hand, when you look at in symbiotic polymers, the functional groups are arranged simultaneously on the left and right as the chain proceeds. You can see there is an orderly arrangement. Then we have isotactic polymer. In isotactic polymer, all the functional groups are present on only one side. So how does the tacticity affect the properties of the polymer? Density change. Now, how does density change in case of this? Is that in case of atactic and isotactic polymers, when two chains are coming close together, if the functional groups are stacked together like this, you can see that it will create a lot of repulsions between two individual polymer chains because of these functional groups facing each other. So because of this, the uh, the polymer chains cannot come together and pack with each other or entangle with each other better. Whereas in case of symbiotic polymer, you can see right here that since they are arranged like this in a proper orderly fashion, a neighboring chain can come close together, and since C double bond group is on the other side, it can attach right here. It can come close right here, and then they can form bonding right here, and then the next polymer chain functional group can attach right here, and so on. So because of that, syntactic polymers will have extremely close packing, because of which the density changes a lot. So uh, next we have makes the chain more flexible. If you are taking the case of an atactic polymer where the functional groups are not present on the correct sides, because of which what happens is that the chains are not entangling together. It means that its crystalline nature is getting affected, and since crystalline nature is getting affected, it won't behave as a proper solid, and it will be like really flexible. Like it won't have solid like properties like extremely crystalline nature. It won't have that, and it will be flexible. Then we have reduces steric hindrances. Now, steric hindrances. What does steric hindrance mean? Since if you take a look at the isotactic polymers, these charge groups are on on only one side, what happens is the repulsion between these groups, individual groups, will be very high in the case of isotactic polymers. But in case of syntactic polymers, if you take a look at this, you can see we have a C double bond O group right here, and then there is no group here, and then the next C double bond O group here is on the third carbon, right? So because of this, what happens is the electrical effects are cancelled out, or else not cancelled out, reduced a lot, since the distance between this is very high. You can see right here. Since the distance between these two is very high, the electrical effects are reduced, and because of that, steric hindrances are reduced. So steric hindrances are reduced, and that's how the tacticity of the polymer chains affects the properties of the polymer. Next, we have a chemical reaction question, and you can see that a certain first order reaction is half completed in 30 minutes. The rate constant for the reaction must be, these are the options. So here you can see that uh, for a first order reaction, uh, we have the standard rate equation as we go for deriving the first order reaction. Since n is equal to 1 for first order reaction, we have n is equal to 1. And when you when you separate the variables right here, we get ln C naught by Ca is equal to Kt. Now, since it is saying that it is half completed, now what does half completed mean? Half completed means that uh, the reactants right here, they have been consumed in half, exactly half. So Ca naught is our initial reactant, and Ca is the reactant at the current stage of the reaction. Now, since the reaction is completed half, so we can say that Ca is equal to Ca naught by 2. We can say this. So if we write here Ca naught by 2, what happens is we can cancel these terms, and then we have ln 2 is equal to Kt. Now ln 2 is 0.693 is equal to K into T. Now we have time right here, 30 minutes. So we have 30 minutes right here. Okay. So if you divide this right here, we will get around something around 1 second. If we divide this right here, we get something around 0.023 minutes. The unit will be in minutes since it's 30 minutes right here. So that's how you solve it. So the rate constant for the reaction must be 0.023 minute inverse. Okay. Since the 30 minutes are in denominator, you will get it as minute inverse. And since Ca naught by Ca was there, concentration terms get cancelled. So we have minute inverse. Next, we have the slope of a graph in between 1 by Ca versus time t in a second order irreversible reaction with equimolar feed concentration. Now, for a second order reaction, again starting from the basics, we have second order reaction. If you solve the entire equation, you will be left with this 1 by Ca minus 1 by Ca naught is equal to Kt. Now, if you draw a graph for this, and what will you see? You will see this that we have 1 by Ca, 1 by Ca, and we have T right here. Okay. So since 1 by Ca, okay, at the initial stages of the reaction, Ca will be almost negligible. It will be less. Okay. And as time goes on, what happens is Ca will start increasing. Okay, as it will start increasing slowly, slowly, slowly. So because of that, what happens is uh, as Ca increases, uh, your Ca increases with time, the ratio will change, and you will get that the slope of that line will be equivalent to K. You can see right here that it's more like a y is equal to mx equation for a line. For a line, you can see right here. So because of that, the slope of the graph between 1 by Ca versus time t in a second order irreversible reaction with molar feed concentration is K, right here, the rate constant. For a zero order reaction system, the rate of the reaction is always independent of concentration, temperature, rate constant, none of the above. So as you can see, for a zero order reaction system, the rate of the equation is independent of concentration. If you have seen the zero order reaction system, what happens is that when you derive it from starting from the basic equations, right from right here, when you put zero here, right here, when you derive it, you will get the expression of Ca minus Ca naught is equal to Kt. So in that case, you can see that initial contents of the reactants are initial contents or the concentration of the reactant is not something which drives the reaction forward. So for a zero order reaction system, concentration term is so the rate of reaction is not dependent on the concentration term. The next we have what is the correct statement about space time and space velocity. Now, what is space time and space velocity? First, we will take a look at this. We have a reactor. Now, we are sending in feed and then we get the product, reactants, and then we have products right here. Okay. So what happens is that what does space time mean? Space time means that if a single batch of reactants is going, example, 1 kg of reactants is going inside. Now, how much time does this 1 kg of reactants spend inside this reactor is what is called space time, and it is denoted by tau. It is denoted by tau. Next, the term is space velocity. Now, what is velocity? Now, space velocity means how many reactor volumes, how many reactor volumes can be treated in one space time is called space velocity. Now, the unit of space velocity is 1 by tau. That is nothing but your space time. You can say minute inverse or second, minute inverse, time inverse we have. So unit of space time is time. Yes, we have seen that how much time does the reactant spend inside the reactor is called space time, so time. The unit of space velocity is time inverse. We have seen right here that how from the basic definition that 1 by tau is the time uh, a single reactor volume takes inside the reactor. So that is space velocity is time inverse. And space time is inversely proportional to space velocity. Yes, space time is inversely proportional to space velocity. Vice versa, as you can see here. So answer would be all of the above. Next, let's moving on. If there is a given space time of 3 hours, so we have a space time of 3 hours. Uh, it means that there is required 3 hours to process one reactor volume to feed to convert it to product. Requires 1 hour to process three reactor volumes of feed to convert to product, and there are 3 hours to process three reactor volumes of feed to convert it to product. So as we have seen from the general definitions of space time and space velocity, we can understand that if tau is equal to 3 hours, it means that one reactor, one reactant package or volume, you can say, is spending 3 hours inside this reactor and then coming out next for it to convert to product. So from that basic definition, we have there are there is a requirement of 3 hours to process one reactor volume of feed to convert it into the product. Okay. Next, moving on, we have what is the slope of the plot of ln K versus 1 by T for a reaction where the activation energy E is positive for the temperature dependency of reaction rate constant given by the Arrhenius equation. Now, what as we have discussed previously also that Arrhenius equation gives you the relation for reaction rate constant with respect to temperature, as you can see. So uh, when you plot ln K versus 1 by temperature right here, as you can see, the intercept here gives you this A. When you apply ln to this, we have ln K, ln is A by T. So we can see right here that this ln A is nothing but your uh, K naught. That is nothing but the frequency factor which comes from the collision theory, which describes that how many collisions are occurring and how many molecules are participating in the collisions for the reaction to occur. That's how it is defined. So this is where you get ln A. Okay. So with respect to that, if you see uh, for positive energy, we will be getting that the graph for an activation energy is positive for the temperature dependency, we will see that the graph will somewhat look like this, and the slope of the graph would be minus E by R. Moving on to the next question, we have the rate of reaction is the function of which of the following options: reacting material, temperature, concentration, and type of reactor used. So from, of course, you must have studied the lectures and you know that a rate of reaction is very much dependent on the reacting material, what kind of material it is, and uh, how its reactivity is with respect to certain temperature or pressure conditions. So you can pressure, concentration. So that's how you relate reacting material with temperature and concentration. So which define the rate of reaction uh, as a function of reacting material, temperature, and concentration. But the type of reactor used is not uh, influential on the rate of reaction because type of reactor is designed with in such a way that we give give the reactants maximum residence time inside the reactor so they have time to react and form the product. It is not as such affecting the rate of reaction. Next, we have choose the correct option from the following statements. In Arrhenius law, the reaction rate constant is directly proportional to temperature. We have seen from the general definition that it is not directly proportional to the temperature, uh, and the relationship is defined as such, as you can see. Uh, so this statement won't be true. In the collision theory, the reaction rate constant is directly proportional to the square root of the temperature term. So in collision theory, we know that molecules are molecules. What collision theory says is that for a reaction to occur, molecules should collide with each other, and as the collision progresses, a reaction occurs. So as uh, as temperature rises, the number of collisions will also increase. So as the temperature rises drastically, the number of collisions will multiply in several orders of magnitude. Because of this, the rate of reaction is directly proportional to square root of the temperature term. Next, we have in the transition state theory, the reaction rate is directly proportional to temperature term. Again, in transition state theory, as we know that the material, the reactants have a certain threshold energy and activation energy, and as they transition from these states, The as they transition from these states to reach the state of reactant, temperature has a big role to play in it. And that's why temperature term is directly proportional to the reaction rate in transition state theories. Collision theory is based on kinetic theory of gases. Again, this stems from the fact that in kinetic theory of gases, study of each molecule, assumptions about each molecules are done, like how they collide with each other, and how the collisions with the surrounding molecules uh, describe the motion of the particles. And since in collision theory we are saying that reaction between the particles is occurring because of the collisions, it is heavily based on the kinetic theory of gases. So these three statements are correct, and this one would be false.